Let's calculate the potential for a continuous charge distribution. And the distribution we're going to look at is a ring. So here we have a ring of radius r, and the ring has a total charge q that's distributed uniformly on the ring. Now, let's in particular look at, here's infinity, where v of infinity is 0. And let's consider a point P that's a height z above the ring. And what we're after is the potential function at the point z. This is what we call the field point, minus infinity. That's the potential difference. But remember, we've chosen that to be 0. And that's our integral now over k dq source over the distance r dq source p. And this is an integral over the ring. Now, we can do this function, we can do this integral a couple of different ways. But first, key point is to choose a source. And I'm going to pick my source over here, dqs. And remember, the key distance here was the distance from dqs to where our field point is, P. And in the geometry of this problem, we can see immediately, without anything special, that this distance, P, is equal to z squared plus r squared to the 1/2. And now that's going to produce a potential function. And we can write our integral now as v on this axis z is equal to the integral over the ring of k dqs over z squared plus r squared to the 1/2. Remember, potential function is a scalar. It's not a vector. Now, as we go around the ring, what is our integral? Well, we're just adding up all these pieces as we go around the ring. And notice that every part of the ring is the same distance to the field point. So the quantities in this integral, k and the denominator, pull out of the integral. And we have k over z squared plus r squared to the 1/2 integral of dqs over the ring. And now, what does this integral mean? We're just adding up the charge as we go around the ring. And that's simply the total charge on the ring. So we have the result, kq over z squared plus r squared to the 1/2. And that is the potential function for the ring along the axis. Now, there's a lot of things we can look at right now. The first thing we want to do is let's imagine the limit in which z goes to infinity. So we're going very far away. Well, let's look at it this way, rather. Instead of z goes to infinity, we want to just look very far away from the ring. So our variable z is much, much bigger than r. Then what I'd like to do is write this potential function. I'm going to pull out the z, and I get 1 plus r over z squared to the 1/2. And I can use my expansion of the denominator to write this as kq over z times 1 minus 1/2 r squared over z squared plus higher order terms. And we can see that in the limit, as z is much bigger than r, this term goes to 0. We have a constant. And our result is kq over z, which is exactly what we expect. Because if we're very far away, this entire ring looks like a point charge. And we're a distance z away from it. And that's the potential function for a point charge, where the point P is a distance z away. So there is a nice calculation for the continuous distribution using our integral superposition principle for potential functions.